Da-da. Hey, welcome to Coffee Compiler Club. We're being recorded. We'll show up on YouTube within whenever I get to it, so hopefully within the day. Um, no set agenda. I do have special guest Rick Hudson here. I have another new person, but I'm going to let Rick go first, and then Louis or Louis, I don't know how to say it. I'll pick on you as the new person, have a 10-second or less. Here I am and why I'm doing it. But Rick, I'm hoping doesn't need too much introduction other than sort of major Go influencer. Um, and you sent me a mail yesterday saying something about Go and GC, and so that's just very much spot on target. Would you like to say something?
Yeah, no, I was sort of chief cook and bottle walk, whatever, for Go's GC, though I must say that I am retired at this point. Okay. So I have no control over what's happening. Okay. So all I can tell you is the reasons why it happened and sort of what we're doing and why we're doing it. I don't want this really to be a technical discussion as much as a, well, why did you do that discussion? I don't know if people are familiar with Go and how it differs from Java. I could give an introduction like that if you want.
I
Uh,
think most people here have some familiarity with Go, and we'd be more interested in why did you do this versus that?
okay. Um, I mean, basically I went to Go because the stuff I was working on at Intel, which was parallel combinators for JavaScript. That was winding down, and the people I was working with were about to go off and build a language called Rust, and I wasn't really sure um, that I wanted to do that because there was no money at Mozilla, I guess. Google, on the other hand, was a good place to land for the last, few decades of my life, or 5, 10 years of my life. Um, anyway, so that's how I ended up there. What did I do that seems like it deserves an explanation of why I did it? Does anybody have any promptings?
Okay, so there's a GC and your multi-threaded concurrent, probably very latency sensitive language for apps that are going to be latency sensitive. There has to be some GC design choices going on here that are interesting.
Okay.
Stop the world versus incremental versus Threadlocal versus.
Okay. Well, we faced the same. Go faced the same problem that Rust faced with their GC at the time, and that was that latency was going to kill it. Okay. Rust took the path of a borrow checker. Brilliant stuff. Um, I did not think of that in time. So nobody did except them, I think. So I took the path of a low latency or no latency GC. Originally, when I presented it to them to start with, it was I'm going to do Sapphire, which was an algorithm that I had invented in part as a response to the work you were doing at Azul and sort of how to do uh, concurrent GC. It's major difference between Sapphire and Azul was probably the fact that it didn't have a read barrier. Okay, and the reason it didn't have a read barrier was that reads, you do 10 reads for every write in these big things. And I felt that if we could get away with doing it without a read barrier, we'd be faster than the fastest at the time, which was your stuff, obviously, for latency. We never really saw numbers from anybody about the cost of a read barrier. It's still sort of a
I
mystery.
can fill you in if you care.
I would love to know how much it. I'm guessing 4%. What, you know?
Ah, it's going to be on the Azul hardware 0 because hardware, and on x86, the numbers I last heard were below that. Although that's getting close to the right thing. It was a few percent. It's difficult to measure below some threshold. There were far more issues involved with pauses that were not GC than the cost of the read barrier. So the people we're talking to, so at Azul's, most money makers would have been high frequency traders. Um, Pauses from the Linux kernel were far more important to beat down than a couple percents from read barriers.
Um, Fair enough. And okay, so why did we? Okay, so Sapphire was completely non-blocking. Okay, we could do everything without a stop the world.
So, same
And
as the Azul collector.
yeah, right. So the question wasn't could it be done? The question was it necessary? And I think we came to the same conclusion you did, which is that if we can get these pauses down to what you typically see from a Linux kernel, then we're done. And
Yeah,
that certainly
we
sub-millisecond and around 100 or 200 microseconds, which is where we
right.
sort of ended up, you know.
So
Yeah,
Azul pivoted from beating down the cost of read barriers to beating down the max pause on the Linux kernel for quite a few years.
right. So, yeah, okay, so thank you. You know, because that clearly had an effect on the Linux kernels that I was using when I wrote this stuff. And so I truly appreciate that. But yeah, so as soon as we sort of got it down to kernel pauses, then we didn't have to complete the Sapphire stuff. And now Sapphire was copying bump pointer type of garbage collector. And we didn't implement that because we had to get it out the door. You know, Go was young, and if Go still had this pause problem, it wasn't going to grow. Uh, and then we got it out, and lo and behold, we didn't have any fragmentation problems, which wasn't a mistake. We did a segregated sized heap
Hmm.
thing, which I had written a malloc package called Intel's scalable malloc, which is sort of Intel's commercial product that they were selling with their multi-core, multi-threaded chips, so they could do high performance C. Okay, so I had a lot of experience with how to do this in C, and I wasn't worried about fragmentation. And I wasn't worried about bump pointers because allocation in Go and Java is all about how fast you can zero stuff. Okay. And not,
That's something Azul did right that I was very annoyed that I couldn't convince Intel to do it right as well. The Azul
they,
hardware did it right.
well, they just added um, no read, zero filled cache line allocation. Okay.
Ah, 10 years too late, 15 years too
I
late.
know, I know. I remember fighting for that for years but it seems to be in there now. And doesn't have to be zero filled. You can actually it's actually a copy thing. So you can actually copy anything you want into that cache line and it's
The,
got
the other thing that happens is that you get barriers for things like final fields that you don't want to interact with these no read lines. You want them, the no read lines, to appear in your cache independent of external blocking memory ordering effects, so that you don't have to have the prefetch of a blank line into your cache be blocked by some totally unrelated fence for a final or a lock. It's a separate memory ordering streams.
no, we didn't get there. Okay. We don't have finals in Go. Okay. So that might be why it never
Right.
Never popped up on my radar screen.
And I don't know if locks are common in Go. Do you guys do a lot of locking? I have no idea.
Uh, we have channels for sharing stuff.
Yeah,
Okay, I think CSP.
right.
Um,
I knew that, but that maybe means you don't lock, but it doesn't necessarily.
well, we do lock, but we
Okay.
don't have locks in every
Well, do you
in every
lock in the
object.
implementation or is the users end up writing locks? Like in Java, users write locks all the time.
Uh, well, again, we encourage people to use, the channels, and so they obviously get atomicity and all the good stuff, and a high performance locking situation. The channels actually write things into other people's stacks. So when they wake up, they're raring to go. Okay. So,
Okay.
all of these really nice performance things, happen there.
Okay.
But yeah,
But
it's a shared mutable memory system. Okay. So yeah, you have to use locks.
but people don't end up writing locks as a matter of course because there's this alternative of channels that probably covers a large set of use cases.
That's the hope. That's the
Yeah.
hope,
Okay.
and I think people that come, people that don't understand channels will go back to what they know, which is Java. Okay. And damn you, but it's, um, uh,
Well, somebody gets there first, and they get there first by not knowing what the hell they're doing and just plowing straight ahead.
yeah, yeah, no, fair enough, fair enough. But, um, uh, so yeah, they're there. But again, unlike Rust, we've got a garbage collector, so we don't have to worry about non-blocking algorithms and allocation. Okay, and that's sort of one of the big wins that GC has that nobody ever talks about. And
Oh,
ABA problems gone. The GC quiesces, so you know that all of the non-blocking algorithms are in a safe spot when you
just to
do
be
a
clear, I
GC.
write non-blocking algorithms that don't depend on that feature of GC, but I know plenty of people who do.
Yeah, I've had to port algorithms that have been written with GC languages in mind. So
Yeah.
like I have a version of the non-blocking hash map from Cliff,
Yeah.
except I wrote it in Java, and that one uses
It
what did I end
uses
up
the
calling it?
GC, but I totally know at every point when I have failed and I have a free object, I just have no way to free it in Java.
Yeah,
So you could rewrite that in C, and at those points you would do a free. And like,
yeah, I
well,
have like an epic based thing where like basically at some periods of time I know that I'm not within a function call to one of the like hash map functions, and because of that, I know that if I were to hold a pointer, it's like exclusively like a new pointer as opposed to like one from like an old call. Because what I can't have happen is like I have an old pointer that I'm still holding on to in another thread. That's like I don't know, maybe doing like a failed operation. He's busy like I don't know doing unnecessary work, but he's still using a pointer that's like real. Like I need to wait until he's done with his call. So I have like a thread that just waits for everyone to be done with their function calls before freeing.
yeah, you're talking about your linker? So,
Uh, the linker uses it, but I do use the non-blocking hash map in a few other cases. But it's basically like I basically just emulate like a small GC that just says like free things when you're not inside of or like once you've advanced the past the function that was using the reference. Because once you're advanced past that function and you update the pointer and then you like advance the function. Once you've advanced past that function, you know that the pointer's been reloaded, so it's not referring to the old pointer, and so you can free it at this point. Once you've guaranteed that everyone's made enough progress.
yeah, I guess I was thinking of the lifetime management inside non-blocking, not lifetime management of the pointers that are passing through it. All right, wait, let's go back to GC and Go.
Yeah. So yeah. So non-blocking pauses. We beat the pauses in kernel. So we've been quite happy with using the allocation um, stuff that we're doing now. I don't think we have zero allocate cache block stuff actually implemented in x86. It's pretty recent. I know they have it in ARM, so there's yet another push there. Um, our bump pointer stuff is we got that real fast. We take the mark map, the bits from the marking from the previous GC, and we just use NSA instructions to find the next unmarked spot in the map, and just grab it. Since it's size segregated, all we have to do is multiply it by something and generate a pointer off the base, and it's actually a bunch of stuff and maybe one more load than you'll find with a bump pointer allocator, but it's very competitive, and and zeroing. It's all about zeroing anyway, so it doesn't make any difference, you know.
Yes. Yes.
But I had to say that because everybody decides that my GC is stupid because it doesn't bump pointer allocate, you know.
No, yeah, I'm with you. It's all about well, it's the cache line miss, so it's all about the zeroing, yes. Yeah,
Yeah,
hard cache
it's
line
not,
miss.
we on big stuff we we point to virtual memory at a physical memory cleared page. Some kernels do this, and on the first write, we'll take we'll take the page fault and set stuff up, but then uh, it's if it's going to stay, we don't have to actually allocate stuff uh, at allocation time in that situation, and clear stuff until later on, and that helps us a little for the for large clearing of stuff, which was yet another one of those. Well, the game you play with a concurrent GC is that you can't have any order n anythings during the stop the world. And I mean anything.
Right. Yeah, yeah.
If anything is order n in there, someone will hit it. Okay. And you may never know that unless you have a commercial product. Okay. But someone will hit it, and you'll spend a couple of years chasing all of those things down. Um,
That
uh,
was Azul's experience as well.
Yeah, so I don't, I hope that my experience wasn't unique. I hope I hope I was right enough to avoid most of them. Um, yeah, so that's that. We tried, uh, every time we tried anything that used expensive write barrier, it lost. Okay, so we're doing server stuff, incomes and requests, banging around, allocate a bunch of stuff, return a few bytes, and then leave the request. If that request is in a single go routine, can we segregate off all of its allocations and then do a Threadlocal GC
Hmm.
as you're about to exit? Okay. And and it worked, about half the time on half of the benchmarks we were running. But we were very sensitive about it not working and coming out with another release that slowed my program down problem, And you're probably familiar
Yeah, 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 yeah.
with that bug report, Um, so it never made it. It's being revisited every periodically.
Oh,
Well,
good.
what if we change the GC API so that they can say, well, here we're going to use that GC and here we're going to use that other GC, and none of that ever composes well.
I
And
fought with a Threadlocal GC at Azul for a couple years on and off, and I eventually could get maybe 70% of all objects allocated stack locally, but it was never, the pause times are too good on the main GC, so it was never really competitive in that sense. And the size of these Threadlocal stacks I was getting were frequently outsize the Azul's tiny caches. So I always have
Yeah.
this lurking question in my head, given an x86 with its much larger caches, could you routinely grab a significant fraction of total allocations, run them completely stack local or cache local, do your cache local GC and at the end and then walk away and never hit memory, never burn bandwidth, kept the throughput for other cores
Now,
alive, that kind of thing.
I'm not sure we were concerned about the cache local aspects of it, though they were important. We were mostly concerned about the fact that if you could do a thread local GC, do all the traces and know what's thread local, then it was inherently scalable. Okay.
Right.
And that was what we were going at.
So
Anyway, it didn't work, but so I burnt a year on that, you know, and and that was good. What else? Go's different than Java in that we don't have we don't have objects. We sort of have pointers, so not everything that gets allocated ends up on the heap or has to end up on the heap, and not everything is. You don't pass pointers to structs between routines. You actually pass the structs by value.
mm,
So there's a lot less, lot fewer pointers on the stack. Okay, and since things are passed by value like that, the pointers to them, if they exist even, uh, tend not to escape the procedures. Okay, and so if they don't escape the procedures, and you've got a bright compiler, you can just allocate them right on the stack. So young objects, generational hypothesis about young objects dying soon. Yeah, it's probably true, but we allocate them on the stack much more than Java is able to because of the
right.
way they pass pointers between procedures. So that's a big win for Java that sort of made it a different challenge to write that garbage collector.
It's definitely a different challenge.
Yeah, yeah, yeah. Let's
So
see
I was
what.
able to, in the thread local thing, I was able to discover that most Java call sites had a strongly normalizing lifetime of allocations. So if a particular method would allocate something at that call site, you could tell with fairly high reliability what stack frame you had to go up to say that when I got to this frame up here, that execution tree included the lifetime of this object, and it wouldn't escape this point in the stack. So if I was allocating it in a frame that was at this level, when I ever exited this frame, it was dead already, and it would been
Well, that's pretty
free.
good. That was without a write barrier.
Yes,
All,
this
all
was
compiler.
the right barrier was there was a right barrier. The right barrier was, I mean, it was low cost, so I didn't kind of care. It would track and say, you didn't haven't escaped so far. I'm assuming you're not escaping. As we leave that frame, I'll
You were getting
check,
all that
make
by
sure
collecting
that nothing.
statistics, not looking at the code, though, right?
I'm sorry?
You were getting that by collecting statistics, not thinking about the code.
Yes.
Oh,
This is escape detection, not escape analysis. Yeah,
oh,
by
okay.
looking at the behavior, using the right barrier to detect that you escaped, I would observe that you did not. So I started by allocating you at a lifetime of this upper frame from, down here, I allocated you in a frame up here because you had a factory, factory, allocate, build, and it, use, but then when this guy left, it was gone. And you would do the last check on the way out that no one in there had lost anything, and then you were done. You threw that frame away, and then immediately reused it the next call in. So you got a stack behavior, but the individual allocation sites loaded things in at different levels in the stack, and I profiled allocation sites.
But they were allocated on the heap.
They were allocated, no, they were allocated in a side stack local area, but not
Okay.
directly on the stack.
Right, right,
In
right,
a section of memory that was stack-like, but not
right,
the stack and not the heap.
right. I think my concern with that would be that that all works for the code you've written, but as soon as you start calling library stuff,
No,
oh, you're just, I see, you're doing hardware counters or something, or
no,
it's all
it,
runtime.
it was done with a sort of a standard read barrier like thing. But I ran shit like JBoss and WebSphere with it. So really
Yeah.
large, complicated apps under heavy loads. Um, and this was a reliable thing. That's because of the way people write code. They need an object for something to get done. They've called some factory to go get them this object. They do their thing. They're done with the object. Well, as soon as you figure out where the the point where the guy says, "Give me it," and then I'm going to use it happens, you found the lifetime, and that can be found with read barriers on allocation sites. I allocate an object here and then I escape the failed the read barrier. So I bump the frame. And the next time I allocated, it escaped to here and it bumped and they got to here and it quit escaping. Then I ran a while and then I said, okay, it's time to go, JIT the code. But I have this and I have, it's going to allocate down here. So I'm going to inline down to here. Now the object's lifetime was in the WAD and it never escaped. At that point, I could have run an escape analysis and probably been successful. But I didn't. I just said, I'll throw in the detector. And the answer was, you didn't escape. So I walked away. Now, what is the cost of the right berry detection? Compare two pointers and jump to a slow path. Well, it's compare pointers. It's highly predicted because you're right most of the time. So it's highly predicted compare and branch. It's half a clock on an x86.
Yeah. I mean, if you don't overflow the instruction cache, inside of some loop or something,
It's a
but
store. You get, as you point out, there's not that many. You get a hot loop.
yeah. So that's okay. Loops. Yeah. The other thing, because of we could never get our loops down to anything reasonable. Okay, when we were looking for a, safe spot. Okay, everything we tried, and we tried everything, didn't work. So eventually, we ended up um, giving a go routine a couple shots at getting to a safe point, and if it didn't fail, then we read our loops were designed. The compiler designed our loops so that we could do uh, asynchronous preemption anywhere inside of the loop. We then went ahead and did what amounted to and it's where the compiler came in. We went ahead and did um, a uh, conservative flavored type of scanning of the
Mm,
pointers to make sure we didn't miss any. Okay. If we got it wrong, no problem. We don't move anything, so we don't have to update anything. We just
mm,
have to make sure we don't miss any.
right.
Okay.
Interesting.
So that's how we got around you guys were talking about this a few weeks ago.
Yeah,
Got,
unroll and jam.
yeah, got around uh, that problem with with how do you deal with loops. Now you've got a tight loop. Your compiler has to know that it's got a different set of restrictions to make sure it can't evaporate a pointer and then come back and reconstitute
So
it.
I can tell you what I did, which was safe point was the compiler had a pointer to everything in the machine architected, the Java virtual machine architected state. So if you stop at a safe point, he can totally rebuild what you would be in the interpreter. And then if the loop is tight, you would unroll. You get a bunch of safe points, but you only need one per loop iteration.
But you have to
So
do the check.
so it's just another piece of IR. You throw out the spares and you have one per unrolled loop body. And then
Yeah.
if the loop is, if that's too much, like the loop's unrolled sufficiently, but you think the trip count's high and the safe point demands the rebuilding ability that puts enough extra code in the loop that you don't like it there, you don't want that safe point anymore, then we went to unroll and jam. So you'd unroll by 8 iterations or something, and then you make a loop around that. and you put a trip count of arbitrary, and then you have a safe point and outer loop that runs the inner one. Well, the inner one's set for 8 unrolled times 1,000 iterations. So it's eating 8,000, then a safe point, and 8,000, then a safe point. So the safe point cost is divided by 8,000, and it just drops down to nothing you care about, can't measure.
I, 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 I was not the compiler person doing this. It was David Chase, if you remember David
I
Chase.
do. I haven't seen
Yeah.
him in decades. I wouldn't mind seeing him again.
Yeah, no, we shared an office
Ah,
for years. It was a
yeah.
it was a fun office. Um, but yeah, so he knew all of these tricks, but he kept coming into the meetings with a sad face, and then we ended up anyway. That's where we ended up, and we obviously came to a different conclusion than you did. I don't know. I remember the Itanium. All you had to do was set a bit, and you could and you had safe points across the whole thing. So that's the machine.
I
A
did the
lot of stuff.
Itanium port of hotspot, and it was not very helpful.
I was gonna say that's the first nice thing I've heard someone say about Itanium.
Well, Itanium. What recently got recently they put re what they call them, reproducible restartable critical sections in the kernel. Okay, you familiar with this concept?
I mean, it
Uh,
sounds like what I would do for any non-blocking thing. You fail out at some point, you just go back and start again. I don't know.
Oh,
yeah,
is that the one like that they use for like what was it, glibc's malloc or something to like make it
yes,
so it's always thread local?
yes. Yeah. There's a direct line between the Itanium and that hack.
Matt, would you put that
Interesting.
link in the doc, please? Sorry.
Yeah, so basically, if the operating system interrupts anything inside of a critical section, okay, it just restarts the critical section. Okay, so no checking or anything, and it was in ITS, the incompatible time sharing system out of MIT in the 70s is where the idea came from. Uh, and then it was so easy to do on the Itanium, that we could sprinkle instructions into the Itanium with a bit set that just said, don't execute this instruction. So all instructions were predicated on one of 64 bits, whether they got executed or not. And so, I mean, they were all executed. The execution was thrown away.
Right. Didn't
Uh,
write back.
yeah, right.
Predicated. Yeah.
And so that was nice to see that come. It made it, that paper about how to do that in Malik was Dave Dice's paper. Okay, and I showed how to use that doing GC allocations in one of my papers.
Hmm.
And then it finally made it in the kernel, another victory. Ideas that you think are dead, resurrect themselves. Uh, so that was pretty cool. See what else about Go that's what might interest you guys? We tried. Well, we periodically try arena allocation because, oh my God, it's so fast in C. Why don't you put it into Go? Since whatever, I don't understand the logic, but it never composes. I was getting to this earlier. You're wandering around in this arena thing, and you call something from the standard lib, and bang, it doesn't compose. So then you have to have two copies of the standard lib, which you're not going to do because that doesn't compose, And so,
Right.
I mean,
so
I've certainly seen a lot of Go code that use an array of structs as a resource pool in an arena-like way.
oh, exactly, and that's another thing that you
Object pooling
um,
by any other name.
can I bitch about shit in this
Yeah.
situation?
Yeah.
Okay, you can do that. and that's a really intelligent thing to do. And the cool thing about it is if you, unlike in, say, Java, if you want to point to a single one of those structs, you can do that in Java, okay? And so it's very easy to say have this array of objects and then sort it without having any extra allocations, okay? And some benchmark programs that want to test how fast you can do stuff won't let go uh, use the trick that we were just told. They said, you can't do that. And so every time people say, well, Go's GC is horrible because but I said, but you could, and they say, sorry, and anyway, so yeah, I'm a bit sensitive about uh, micro benchmarks that are seem
So
to be designed for somebody else's
yes,
GC. And even
I
though Go knows
fought
how to make it faster than them, we don't, we can't,
right.
we lose their silly games.
I fought the micro benchmark wars with Java versus C for many, many years, more than a decade. And there were things like your sign function sucks because you're not using the Intel partial sign, which has all these wild edge cases where it just fails on and gives crappy answers for. But if you called some version of C and sign and did -02 or '03, it took just the one instruction, which was not IEEE 754 compliant and had all these edge cases it failed on, but you weren't doing that, so you suck. And you
Yeah,
had to fight and say, well, no.
I remember we had to store and reload floats
Yes,
memory
yes,
because
because
we had too many bits in our
yes, you didn't get
floating.
rounding correct.
And we were just okay. This doesn't. It's okay. So
Right.
yeah,
Exactly. No,
you remember
I exactly fought that one too. Hey, I'm using the 8087 because it's
that?
pre-SSE and I had 80 bits precision. You're wrong.
I know. Anyway, that was sad. I was on the other side of the Intel bench at that point.
Well, so the next one, now you got me on micro benchmarks. The next one would be it's a JIT system. So these people would run these benchmarks that would run in a tenth second on the x86 of the day. Okay, well, I can almost get the JIT in there in a tenth second. And then did you really care that your benchmark ran in a tenth second and mine ran in 2/10? So then there was the set of folks that said, hey, we'll just time some 1,000 iterations or 10,000 and decide this is how fast you are roughly, and then we'll do a real timing run. And so they would time it and it would be running in the interpreter and they'd say, you suck, you're slow. We'll run you only a small number of iterations afterwards. Those would run JITted and the JITted would be done. And that was below the timing threshold on the machine of the era, which was only giving you a 10 millisecond or 100 millisecond clock cycle, whatever Windows and somebody had a very narrow thing. So you either got 0 or 1 clock tick, 0, 1 of the millisecond counts. So you basically had a random number between 0 and infinity that he took for the time. And then he would roll it into a geo mean. And then the geo mean would be up or down by some huge amount based on randomly you got a 0 or 1 out of a clock tick.
Yeah,
Ah,
yeah,
geez, dudes.
yeah. I know. I mean, Jesus, sounds like we're talking 20 years ago, Cliff.
Yes, well,
There
you
was
said
a
micro benchmarks, and I'm like, oh, I fought those. I remember those.
Yeah,
there
yeah,
was a
yeah,
fun
yeah.
demoing trick that the IE8 there was someone on the IE8 team who had a real knack for designing example sites that would run really well in IE and really badly in Chrome and Firefox.
Ah,
And they were very fine-tuned. It was things like we go megamorphic at 8 and they go megamorphic at 4, so we're going to have 5 versions of each class. And if you're really
Gotcha.
designing a thing to go smoothly on IE and badly in Chrome and Firefox,
I,
there's an interesting art game to that.
right. I claimed that the benchmarks I was looking at weren't designed to screw up in a JITted system. They just happened to screw up in a JITted system. So I have to throw
There's
one more out, and this one was some fairly well-known academic person was running, how fast is your locking? And I will do uncontended locking as one of my benchmark runs. And so how fast is uncontended locking? Well, at the JVM at the time, would look and see that you never launched a second user mode thread. So he would just throw away all locks, period.
Yeah, right. Of course. We did that.
Okay, fine.
But
But that's not a
yeah.
hack. That's going to be really beneficial to serious production systems in the world.
That only ever launch the main thread and never another one. These days Java launches finalizer threads and this and that, and finalizer should have been shot long ago anyhow. But yes,
Sorry
So
about
your
that.
argument is there's no such thing as a single-threaded JVM these days.
that's not for a long time. Yeah.
Yeah. Well, you might
There's
have a single CPU. We triggered on the CPU, not the number of
hmm,
threads, and we use caches, and so anyway, what was I thinking?
go.
We're not JITted, okay?
Yeah.
We have way ahead of time compilation or JIT, which was once referred to as better late than never compilation, which I thought was funny.
Java generates really good code because all that profiling data lets him do all kind of fun things. It's like you're running a profile
I-
guiding
I'm a
optimizer every time.
I'm a
It's the same.
disciple on that argument, and I hated JITs for years because I was on uh, the smelly end of the stick when it came to trying to write reproducible bugs on my GC because the code underneath me kept changing. It was constantly seemed unfair to me, So
So what if
that's
we
As the
turn the
guy
Go
who had to
question around
debug
and
the
say,
compiler
go,
bugs, let me tell you about code moving out from under me while I'm trying to figure out what the hell's going on.
well, there you go. Fair enough. Well, what was it? We
but
moved
Go does
code.
compile a runtime into every binary. What are the things that Go puts in the runtime that you felt couldn't be done ahead of time?
Well, you've got a scheduler, okay, and we've got a garbage collector, okay, and then we have, I don't know what you call the runtime, but we have a whole slew of standard libraries that get there.
Anything to
Um,
do with channel management? I guess that
well, yeah,
relates to
the
scheduling.
channel, I don't, we must have, yeah, we must have some channel stuff in there, but a lot of that's burnt into the compiled code. Okay. You don't want to be calling out of the compiled code to do channel stuff. That's got to be
It,
fast.
you
Okay.
usually would have backflow issues at some point that I would think might lead you to.
Well, we have,
I'm trying to throw something on that channel. He's not picking it up fast enough, so I'm out
well,
racing him.
you can throw so many things on a channel before we tell you to stop.
Right.
Okay.
And to tell you to
That's,
stop doesn't call into some runtime thing.
no, it just doesn't complete your
The
your
generated compiled
push.
code hits some
Your push
blocking.
doesn't complete. Okay, your write into the channel or read from the channel,
Yeah.
just the compiled code just doesn't complete until it can. Okay.
So I mean, so it hits a block and it goes into the OS and says this thread blocks because he's trying to
Well,
write to a full channel.
no. I mean, it'll do your normal exponential back off before it ends up, doing, you know.
Okay. And that exponential backup is compiled in, or is that a runtime thing?
I'm sure it's compiled in. Yeah.
Wow. Okay.
I mean, or maybe. I don't know. I don't know. But our compiled code tends to have the procedure that counts and then has this tail down below of stuff that we never go to. I assume
Yeah.
everybody does that,
We have the what we call the millicode, which would be the compiled in. I'm spinning to get a hot lock. I failed. I go to the millicode. I start counting how long it's been since I've able to get this lock, and then I might change locking strategies at some point. But that millicode, as I would claim, is part of the runtime and not part of the compiled code.
I don't know. I actually
Right.
don't know.
Yeah.
I do know that we Intel just M-weight, what was it? Monitor M-weight. Remember those instructions?
Yeah.
Uh, they now have that in user. That's now available in user code or
But
user mode.
usually if I'm starting to head down the path where I'm going to block or wait, I go tell the OS so that he can or the runtime, you can count up another thread. I'm about to lose this thread. I need a new one.
Yeah. I don't know. I think what the monitor MWait does is you monitor a location, and if that location changes, the MWait continues executing your code.
Right.
Okay, so it's low power, or it actually causes a hyperthread to swap in the hardware.
I'm about to say it's going to be that. That's the thing. I'm running 100,000 runnables on a 64 core machine. I'm about to block a core, which is a thread. I want that core busy doing something else. So at the time that this thread goes to sleep, I'm going to wake up somebody else.
Yep, yep, yep,
And I
yep,
need
yep,
the wake up to happen before I go to sleep.
yeah. But you don't want the problem was you don't want to use energy in the spin. Okay, when you are spinning before you go out to the OS, unless you're letting the OS do the spinning for you, which seems silly. You know,
Well, okay. So I just kept my
you want to
spins. Yeah.
spin half a dozen times.
I,
Before you actually give up your
I would keep a count and not spin very long.
yeah, right, and then you go to the OS. Fair enough. Or
Yeah.
you release,
Yeah.
maybe not go to the OS, but at least release the
Right.
we're green threads, so we wouldn't go to the OS to swap the threads. We would
Right.
just
And that varied according to the age of Java as to which versions. And then in some cases, I'm using green threads. In some cases, I'm not.
no, okay, yeah, yeah. Uh, so job we have 2K stacks. Okay, this is an interesting thing
Hmm.
that people don't know about um, Go. So we have 2K stacks. So you fire up a Go routine, which is just a fancy word for a coroutine, and you get a 2K stack. And if you overflow that stack, um, we will copy the stack to a 4K stack. Okay, so we actually have to have a lot of mechanisms for doing a copy collector in the system, but we use it for stacks instead of the heap. Okay, so we have to know if we have pointers into the stack, we have to fix them when we do these copies. Okay, and you go to 2K to 4K to 8K and so forth for the stacks, which is how we keep our stack size um, fairly low. And we don't have to have a full OS stack for every thread that we're running.
The Azul collector on x86, we went to large TLBs, those are two meg maybe stacks, but you would break them up into 4K pages, and so the actual physical memory would be whatever 4K pages were active, plus guard pages at either end, and a Threadlocal this and that. There's a couple of extra pages lost. Um, but you just
So
TLB'd your
just
way to
you would
smaller
burn virtual
stacks.
memory, and since you're now 64 bits, it wasn't a big deal.
Right,
Yeah,
right.
fair enough. Um, that's not where we landed. I can't reconstruct where we landed, but I think it was probably TLB stuff, you know.
Right.
Uh, and we just ran out of TLB, and that wasn't a good thing. Yeah.
Well, we did go to the zone of if you're winding around furiously in your stack, then we'll just leave you at the fat 2 meg TLB, and then you won't burn another TLB slot for your entire stack, but you'll have to lose the full 2 megs
When
for
you
your
lose,
OS for
right,
your OS
right.
stack.
Yeah, I don't know what Go does
Okay.
in those. I remember conversations, but I don't know where it ended up.
So the
Yeah.
other thing that came out of that was if you took, since it was always a 2 meg aligned boundary for that stack pointer, you could shift it right by 19 or something, and that was your thread ID.
Oh, okay.
So that was
We
a
Go doesn't have Go routine IDs. Okay, that's something
hmm.
else. So if you want to do some kind of a you use a Go routine ID to
Well, this Go routine has a collection of other Go routines, and he wants to start and stop them. I mean, I don't know. As soon as
Right.
Java has thread executors and they're managing other threads, he has an array of threads he's managing.
I don't know what I
Yeah, it's
can't
funny.
speak to that, you know. Um, uh, the one thing that the Go routine, the Go, I don't, he must have had this in Azul, but we spent a lot of time doing the math and everything for a feedback pacer, so that we can nail in a steady state, we can nail exactly when you want to start a GC, and
Yes.
we'll know that we'll
Yeah.
finish it on time
Yep. Yep.
in the steady state, and
That
it's
was Michael
it's
Wolf did that
amazingly
work, but
good.
yeah.
What?
Michael Wolf did that work, but there are many Michael Wolfs in this field. The particular one I'm thinking about is whatever. He lives in San Francisco, and I see him on and
Okay.
off every year. Yeah.
There was even a Michael Wolf at UMass in Colorado.
Yeah, not that Michael Wolf.
Yeah. Okay. All right. Oh, there, and I had so much respect for him. Anyway, for the UMass one. Uh, yeah. Uh,
Right. So you had a
yeah.
heuristic that said, I'm counting how fast you're consuming and when you're going to run out, and I backpedal, and before you're going to run out, I start the next cycle.
Right.
Yeah.
And if we blow it, if there's a phase change in the
Yeah.
code, which there always is, we, at one point, uh, we would check the allocator. So if you ever needed another block from the central
Yeah.
block storage, we would check whether the garbage collector is getting behind. Okay. And if it would, we wouldn't give you your, this wouldn't be just for one allocation. We'd be giving you like, you know, 10K or 16K of space. We'd make you do that much work
Mm.
assisting the GC. So if you're the guy that's causing the GC to get behind, we make you stop and catch the GC up. Okay.
The Azul collector does much the same kind of thing. Certainly, threads crawl their own stacks and do their own marks, and they're all independently safe pointable from each other. But if the GC is getting behind the thread that causes the trouble, Mike did something there, and he may have blocked a guy and then picked up the core to go run the GC, as opposed
Yeah.
to having the GC go be deep in his stack and try to go do tracing collection on behalf of something unrelated. Like it was never worth it to have a thread who's running and doing things and allocating and is busy making trouble by allocating too much stop and change to a whole new task that's not in his iCache and none of the pointers he's chasing are in his Dcache
You
and
just
have him
stop it.
go try and mark. So instead, you'd rather have a GC thread go do that. But you could stop a guy who was just the dude causing trouble running out and then go collect a while and then give it back. We had a better way. We could free memory fairly easily, fairly quickly at high CPU cost, and we had all kind of extra CPU. So we could pick a page that we thought was we had a sorted list of pages of densities of what we knew was going to be live or not, and we could take a page of whatever density, take the live stuff out, declare the page free, remap it in the TLB, and hand it to you. And so the cost to empty a page was copy out a handful of live things. As you got behind her, the next page you could grab hadn't been collected or counted enough, and so it had more things to be moved out. So you would free that page by copying more things. Now it was still fairly quickly, and you could hand the page off to the dude. But as you got further behind, you burned more cores to free up these pages that should have waited longer before they would get
Yeah.
collected.
Yeah. 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 Well, you would then what? You would take the TLB miss and then patch up the pointers that used to
Yeah.
go into that area.
Yeah, yeah.
Yeah. Right.
We burned a pointer in a TLB mirroring, and if you were an out of generation, your TLB would trip you, and then the core that tripped would patch his own pointer up,
Wonder, sure. Yeah, it makes sense. Yeah.
and he would then take more TLB misses for a little while, but not very long, and then he'd be back to sort of steady state.
And then you would, at some point at the end of the collection, then you would know that there's no more pointers left into that
Right.
page,
And then
and you
right.
burn the page or the
Right. But you
TLB.
could free the physical memory early. You could say this thing
Yeah,
I'm
yeah,
gonna
yeah, 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 yeah,
okay.
yeah, yeah. Because you took the miss
Yeah.
to solve the problem. Right,
Right.
right,
Right.
right, right, right.
So you
Yeah,
got the memory quick. The fix up came over time. At the end of a cycle, you freed the virtual memory as well.
yep, 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 yep. Cool. Uh,
Well,
oh,
you wanna take a break and let me
sure.
intro. I got one or two new people, and then maybe conversation can go where it goes, or we can come right back around if you got more stuff.
Sounds like a plan. I don't have,
Right. Yeah,
I'm
you
just
just
here.
short notice. I've
Well,
done this
I
before where people say, hey, senior people say, hey, can I? And I'm like, sure. And then it's 2 months before they show up.
I'm
You're under
retired.
24, so it's pretty quick.
I've retired and it's too cold to go kayaking, so here I am.
Gotcha. Um,
I don't
Lewis or
usually
Louis,
hear
tell me your
compiler
name and
discussions as
yeah.
an alternative to kayaking, but I like it.
Which one? Sorry.
I don't usually hear compiler discussions as the alternative to kayaking, but sure.
Gotcha.
On cold, windy days they are. Okay.
Lewis, go.
Yep. Hello. Unlike Rick, I'm very much not retired. And so, yeah, I found you guys on YouTube, actually, kind of randomly. And I thought it was super interesting. I've been watching the past like few streams, and I thought I'd join. I'm very much interested in the compiler space. I work mostly in Go, actually, interestingly, and in Rust too. And so Rust C is it's kind of like where I started compilers, but I'm by no stretch of the imagination an expert. I'm really getting started here and I'm just trying to learn really. So yeah.
Okay, thanks.
Cool. Welcome.
Um, who is Corey? Have you done the intro before? I don't remember. It's been a while.
I think Corey did
You think you
intro
did?
a couple of weeks ago. Yeah.
I did, yeah.
You
But
okay? Now you have a video, and I see your
sorry.
face. It's all good. And let me grab Klaus, who maybe was the first time. I gave you an invite a while ago.
Oh, hey. Yeah, I've been on this podcast, but it was like maybe 2 years ago. But I I've been watching a bit on YouTube. So I'm a PhD student and I'm researching a bit about programming languages and like distributed systems. So we are trying to create a language for kind of data streaming. But it's very interesting to hear the discussion about the Go because I mean I'm trying to take some inspiration from Go and other concurrent languages.
Yeah,
Uh,
cool.
Cool. Welcome.
Thanks.
I must say I love your surname.
Oh, it's Swedish.
Ja, ja, ja. Jag kan förstå lite.
Where are you? Are you from
I'm
Sweden?
Finnish.
Oh, cool.
All right.
So if your language is about stream processing, have you looked at Erlang and some of the other big distributed languages? And what do you think?
Um, yeah. I mean, I know a bit of Erlang. At my university, we teach a course about it, and my language is maybe more like restrictive, so it's easier to make it like fault tolerant automatically, or a lot of stuff is meant to be managed for you, so maybe it's not as flexible. It's more like a bit closer to a query language than like a general purpose language.
You have a link?
Yes,
You got the
it's
Google
like
Doc open? You can drop it in the link section.
sure. I can show. We submitted a paper like last year, or I mean, we published a paper in a conference, so I can put it.
Yeah. Or drop it in the chat and somebody will copy it into the link section. Either way.
Okay. I was wondering, have you discussed e-graphs and like equality saturation? Maybe I've missed it.
I'm sorry, fee
Uh,
graphs?
yeah, the equality graphs for like optimization.
So graphs, equality graphs. I do optimizations with classically called common sub-expression elimination.
Mm,
That would be equality between two individual points in a graph. And
mm,
then my thesis includes equality done more or less with a super extended version of the DFA minimization algorithm. Break things up into equivalent partitions and keep breaking it up until the partitions are actually, everything in a partition is equivalent. Is that what you're talking about?
Um, maybe like it's a bit related, but e-graphs are like, or
Oh,
someone beat in the chat,
e-graphs.
it's just like a very general data structure for implementing optimizations.
Right.
Um,
So there have been people who talk e-graphs on here. I will do sea of nodes, which is a very, in my opinion, a very general purpose
mm,
graph format for doing optimizations on, and it is not e-graphs.
mm.
There have been people who talk e-graphs on here, and I'm not the e-graph person.
Okay, but interesting. I will maybe search a bit in the
I have a tutorial
YouTube.
on sea of nodes I've been putting together called Simple. Maybe somebody can throw the direct link in as an alternative to eGraphs. Oh, Matt's been busy on Discord. Oh my God. Yeah, fine, I'll get there. Yes. Okay. If you
Not
want
super
to,
familiar with the term egraphs. This is to accomplish common sub-expression elimination. I've already calculated this chunk, and I know that chunk is equal, so I don't need to redo that work.
It's really for equivalence relations. So it started first in SAT solvers. That's where it originally was implemented because in a SAT solver, you have to churn through a lot of equivalent expressions like A and B or B and A. And these are completely equivalent or interchangeable. So we'd like to have an efficient data structure that allows you to store that they are equivalent and use this equivalence for something. And because compilers do related things with equivalent expressions, like, for example, common sum expression elimination, it turned out to be useful to also have that kind of representation in compilers.
yeah, I'm certain there are a lot of overlap.
There's like the crane lift compiler. It's like an alternative in the future maybe to LLVM IR. And they use eGraphs or like a modification of eGraphs. Um,
I'm copying links
uh,
here, doing management things. Um,
There's a lot of works also in database query optimizers that attempt to do something similar, so-called memo tables, which have been pioneered in like 1980s or something like that, if not earlier. Like if you are considering multiple join orders for a query, joining A with table B or joining table B with table A in some sense may be equivalent. At the same time, the optimization, it depends because depending on the merge, so the join algorithm, it may be better to merge smaller table into larger or not.
mm,
So there's been a lot of work to actually optimize that because the number of those possible join orders for a query
yeah.
grows something like a Catalan number times a factorial, which is an insanely high growth. So the more you can prune, I mean, it's similar in SATSOL, but you also have obviously NP, algorithmic
mm.
complexity. So the more you can prune, the better. I always wondered why the database literature, SAT-solving literature, and compiler literature don't have more of an overlap because there's a lot of similar problems those areas solve. I guess there's only 24 hours in a day, and that could be one constraint.
I
I
think
think it's
I think
been a
it's
little,
more precisely about time than that. The SAT solvers are willing to use tricks that require a lot of compute, in order to make a totally untenable amount of compute go away. Whereas the databases tend to really want to get your database query compiled in milliseconds so that they can get very fast turnarounds on queries. And they're not interested in an optimization that takes something from heat death of the universe to 3 days. They're interested in an optimization that takes something from 3 seconds to 3 milliseconds.
And then in compilers, JITs are on the one end of the one end where you just want to get there fast, and AOT compilers will, happily take some more time to do the same things but better.
I think
don't get me wrong, I'm happy when my sat solver comes back in 3 days instead of heat death of the universe, but
AOT compiler, not so much.
Yeah, 3 days is a little long for the AOT.
Yeah, it's especially ironic when an ahead of time compiler takes like, some double or 10x the amount of time just to produce some output that's like just slightly better than what you could have produced in like, significantly less time.
Yeah, C2 will be 1,000 times faster in LLVM and only slightly slower unless profiling has kicked in, and then it's frequently within measurement error on both sides as fast. That the profiling data moves it from I got there quick to and also I'm better.
Yeah, the heuristic I used to hear from people was for every 10x you make your compiler slower, you can make your code 10% faster.
Nah, that was what I got when I was a grad student. Headed up from grad to late Java era, so I don't know, the 2000s or something. And then I'm watching over time, and the code quality speed come out is not actually really improving very much.
We get better than that. We are roughly an order of magnitude slower than C2, but on the set of benchmarks that we track, about like 600 tests, it's about 35% fast on the geomean.
And you have the profile data.
Oh yeah.
Yeah. The LLVM does not, and I'm claiming if LLVM got 10x slower and no profiling data, it is not going to get 10x or 30% faster. No. No, I think you've done a good thing there, Arthur. That's an impressive amount of speed up for the cost that you pay to get there. But I haven't seen that come anywhere else.
Yeah, but I think it's not quite fair to compare C2 with profile with LLVM without profile. And what we do is much more
Except that that's how people use it.
Except that's how people use it. Yeah, exactly.
Yeah, in practice, I imagine most C++ programs compile without profiling data.
That's right.
And they especially don't have dynamically generated and on the fly compile time, profiling data.
Right.
You might have recorded a few idealistic cases, but they're not going to have inline caches or anything fancy like that.
To be fair, if we are talking about how most people use things, then most C++ applications are interactive. So you start up Chrome and you want to Chrome have running, which means that we should compare Java never warming, never giving it warm-up time. So it's not going to have any profile data either. It's probably not even going to get to C2 by the time the C++ program has started up.
Well, I actually don't think that's true. I think that for the majority of even for interactive programs in C++, it's not like they're being spun up for microseconds at a time and then spinning down. No, they stay on, which means that they're running the same code over and over again. And especially these are the ideal cases for profile guided stuff. It's like, oh, you have a game or something, or you have a UI. It's like, well, it's running a lot of the same stuff every single frame. Or let's say it only runs it every single time it needs to update the screen. It gets dirty or something and it decides to update. Cool. Same graph walks of whatever UI updating stuff every single time.
I think that depends. Most applications, I mean, at least the ones I was thinking of are Linux command line applications. I launch an editor and I close it. I don't keep it open. I launch a debugger, I close it. I run C++ compiler session with Clang++ and I close it. And I really care about immediate low latency startup.
So I launch
or I open game and I close the game, and I will not keep this game running in the day when I'm not playing this. So again, I care about low latency startup.
No. Yeah, and that makes sense. But you're still talking about long running things. Like a game, you're not running a game for 1 second. If we're talking about 1 second runs, okay, maybe warm up is going to become a problem. But if we're talking about you play a game for 20 minutes,
yeah, I think that's a good point. That the game
nothing to do with compilers. It's the disk.
Yeah,
you're far slower to disk than you are to JIT. The JIT's quick. It's all done in a handful of a fraction of a second.
We know what takes a long startup time in game.
LLVM.
shader compilers, and
Yeah, but
shader
that's
compilers are
LLVM's
JITs.
fault.
Yeah, that's not Java's fault. Yeah, that's
Yeah.
shader compilation.
Yeah,
Yes.
the issue is basically you probably shouldn't write like fast compiling JITs that you want to run a bunch of like tiny like instances of with LLVM.
Yes.
I do sometimes wonder, though, if you would benefit from continuing to look at counters after you've JITted the really hot versions of things and
Yep.
say, it appears my assumptions have become invalid. Maybe it's time for me to reJIT this, which it seems like Java C2 at least doesn't really do. Once it's gotten to its sort of optimal, most optimized thing, it just assumes the world is going to stay like that.
Yeah. If you trigger a new class load or one of the deopt events, you'll force a reinspection of the profiles. But if you don't force a reinspection, you're correct.
Right.
But that's
So
not
I'm
really
gonna
C2. That would be the runtime saying, I've noticed the counters have drifted. It's time to kick C2 again.
So I'm going to give a half incorrect story because I'm telling a story that I heard as a story. I didn't do it myself. But Twitter used to have very different performance characteristics during World Cup games than during normal moments. Because you get these huge spikes in traffic when very large numbers of people decide to treat goal with lots of O's in it all at the exact same time. And in order to deal with those huge spikes, it would do things like switch to much dumber algorithms for the machine learning to decide which ads to serve you. Because serving you a bad ad immediately after a goal is kind of irrelevant. Your stream's exploding anyway. Like, you don't need to be super targeted at that moment.
But you probably
But
get
the
a
side effect of that was,
you get a car or
performance characteristics changed a lot in those really high traffic moments, and it had been compiled for not that. So it turned out that if you had, say, 90% of your servers that were just running and 10% of your servers that you kept rebooting every 10 minutes during a game, those 10% would get JITted in the environment in which they were actually operating and handle that particular spike of traffic much better. And those 10% of servers could do as much work as the other 90%.
Wow.
And there were some times where having servers that got rebooted on a tight cadence to forget and reJIT were giving more performance than the ones that had been up for 2 weeks. Whereas in normal operations, essentially the longer a server had been up, the more performant it got because more of the code was JITted.
Interesting. Well, there's definitely an asymptotic curve. So
and again, I've heard the story. I haven't seen the hard numbers on it, but it does make me wonder.
After 10 minutes, you weren't getting very much JITting unless you phase changed. And if you've been up for 2 weeks, you're obviously not getting any JITting.
Right. What you wanted to do was reboot that set of servers immediately when a goal happened so that they warmed up in the post-World Cup goal environment. And then you had 90% of your servers being normal and 10% of your servers being post-World Cup goal.
That's very funny. I would have not thought that was that much performance difference.
And again, like I can't prove it. I haven't seen the real numbers. I've only heard the legends.
Yeah,
so.
it does say you can JIT substantially within a few minutes. You're like running as fast as everybody else in just a few minutes. And in fact, I would claim you're probably running within seconds, other than disk and cache is missing. Nothing to do with code. Fine.
But we had a lot of experience where it was just enough to make me wonder.
Right.
If there are ways to detect good times to forget your JITted code and go again.
Well, there are a lot of papers on there were papers historically when the JITting thing was first hot coming out. There were a lot of papers people were doing about phase changes and when did you optimize this and that and how do you get stable behavior? And the answer was, well, the load wasn't stable, so the behavior wasn't stable. And then you'd get these sine waves of performance in running systems that turned out to be somebody was trying to phase change and then deopt, and then they phase change and deopt the other way, and they never quite caught up. But that was because they didn't ever swallow the whole double repeated set of phases in one compilation.
Yeah. I guess.
Do you think it's probably the right move to just JIT and stop?
I guess like method JITs and like continuous. Every time you run a new block with new parameters, then you JIT it again. Like that kind of stuff would then be a viable option here, which I kind of mentioned a couple of weeks ago, I think.
Same. Once it's captured the one time on the parameters, it's done what it's done. But if there's been a phase change in the meantime, so while the parameter might be this, the actual value is always null versus not or whatever. You have different code.
Yeah, I guess it
Your trip
depends
count
on
of your
kind of
loop was
how
under
yeah.
10 typically, and you didn't bother to do much. And then it's goal, and then it's now 100,000, and you want to do something different.
So I don't know if you've ever run a Clojure web service.
Web servicing Clojure? No.
Yeah.
No.
Clojure has a big standard library, and most of it's written in Clojure, so it takes it a while to sort of bootstrap itself up to running warmly. So I do sometimes wonder, do most JVMs running Clojure have JIT-did code that is really optimized not for the true workload, but for the bootstrapping process? Because everything,
Depends on how
like the
long it
bootstrap was
runs.
definitely long enough that the JIT kicked in, and
Right. Yeah, it depends on how long you run afterwards. Like the sort of typical response for these, I had C2 kicking in during startup, was by the time you hit steady state, the startup code wasn't running, so the JITted code didn't matter, so you didn't care. Or you hit something new during steady state, and then the JITted code got rejitted because you blew a deopt event, and away you go. There were cases in micro benchmarks I had to fight where people were, hey, see ya, Yasser, were causing the JIT to happen during some warm-up piece of the micro benchmark that was then suboptimal during the benchmark piece. And a bunch of those issues kind of got beaten down over the years because the micro benchmark crowd got so verbose about it for no good reason. I guess the most famous one was the first time fast, second one slow. They were like, I have this version and I'm going to run it in a hot loop and time it. And then I have that version. I'm going to run a hot loop and time it. See which one's better, which one's faster. And the first one comes through and says, well, I've never seen any other class here. So your abstract class is clearly the version 1. So I'll just inline the version 1. Now you have a hot loop doing square roots of the same number in version 1. It's all loop invariant. I'll throw the code away and print an answer. So it's 10 milliseconds to profile, 10 milliseconds to JIT, 10 milliseconds to run and get an answer, and you're done. And irregardless of trip count, it was 20 or 30 milliseconds, and here was your answer. And you scaled by your trip count and got a giant thing. Then you're on the second version. He says, oh, now I'm megamorphic. I go to 2. So I actually have a function call, has a virtual call in it. It's 100 times, 1,000 times slower because it's a, hot code with a virtual call in it. And then you got a giant different number and you said, oh, this version's super fast. This sucks. Don't do this other guy. But if you reverse the order of those, then the other guy would be the winner and get super fast. And they never reversed the order and they didn't catch that. And that took a while to get people to sort on how to profile. These days, you grab one of the, J caliper or whatever. There's a bunch of tuning JVM profiling things that are smart about JITs on purpose. So you can JIT small individual instructions and profile them well and get the real answer out. But yeah, there was definitely an era where people screwed that up and then they would get up on big conferences and say, do X, not Y, because it sucks. And I would have to ask and find out that they just fucked this one.
My personal very personal experience with like how JITs lie to you and how non-JITs lie to you is there's a website that runs multiple different JavaScript engines each single night, testing the test 262, so the conformance test of JavaScript on these engines. And my engine is one of those on the list. And for some reason, which I'm not quite sure about, but for some reason, my engine is often the one that runs the fastest, about twice as fast as like V8, which is like, yes, I'm totally twice as fast as V8. That makes a lot of sense. I'm sure that's the case. And I have actually kind of like taken a mild amount of pride in this, but obviously it's total bullshit.
Don't look too close. Yeah. You haven't sorted it out yet? What's going on there?
I think it's half that just a lot of the tests fail so quickly. There's like instead of allowing the code to keep running to the end to then print out an error, it actually panics. Says, this function hasn't been implemented yet, panic. So that's probably one part.
So it's in the same direction of the dev null is a very fast file system.
Yes.
Yeah, right. So the test goal is to get a failure. So if you just fail everything immediately, you're super fast.
Yeah. Though there was actually another engine there that did fail every single test and it was still slower. So maybe maybe there's like this bit of chance that my engine actually is a slight bit like relatively fast. I don't know.
But if it's going to fail anyhow, maybe it doesn't really matter if you fail quick. I mean, it's useful to
Yeah.
fail quick.
Yes, very, very much so.
I was going to say, quickly realizing that you can't do something is a thing to be proud of.
Yeah, yeah.
Though I would say maybe a potential user would be very angry when they're like, you see, you ask, like use feature detection in a way to ask, does this function exist? And the engine says, yes, it does. Go ahead. And you call it, and the engine panics. You'd probably be angry at that.
Well, I would claim that was a failure of the test as opposed to a failure of the engine per se. Yeah.
I mean, if the engine's implementation of that function is that it panics every time.
Yeah, I would claim the test ought to fail you and not pass the test because you failed, but fail you because you failed to fail in the correct way. God. Yes, I have
That was
negative
a
tests in simple, and they're kind of a bitch that you fail the correct way.
that
The
was a
parser comes
famous
along
not
and
understanding humans failure at YouTube. Was they put in this rule that said you for every single div that is visible to the user, there has to be an ARIA tag so people with the screen readers don't just get it's a button. So they put in this enforcing rule that meant that all this stuff had to have ARIA tags or it wouldn't let you launch your service. So what was the situation 3 days after that? Is there were huge numbers of buttons across Google platforms that if you put your mouse over them said to do bracket name of some developer close bracket insert ARIA string here. Because developers were like, oh, there's this new rule that says I have to put something in this field. I'm just going to go generate to-dos for all those things and clean them up later. And the user experience got way worse than just saying button if everything says to-do, put description of item here. And it was an example of a cultural failure because they did not successfully explain to the developers why the system had just blocked them from deploying.
Excellent. All right, what else? I'll do the 10-second simple update, and then if there's not gonna be anything else, we can walk away. Went to Java 1, burned a lot of time. Then encoding is down to like patching. So relocation patching, stack frame sizes are computed, and the spill code gets its offsets patched. The ELF files are getting generated. I think with a little more screwing around, we'll declare the end of chapter 21 victory, and we'll be generating proper ELF files across the board. I don't even know what the hell to do after chapter 21. There's a thousand cool things to be done. Probably we need to sort allocation after chapter 21. So right now I'm using the epsilon allocator where you allocate until you run out of memory. And there's no free, which is all good for this kind of thing. And for Rick's sake, my long-term goal here is to have strings be buildable within the simple language directly. That's not happened yet, so we don't have any strings either. So I guess native IO calls, strings, and allocation are like the big ticket items that are missing from the implementation here. But yeah,
There's
it's got
one thing awk taught us, it's that you should have strings natively.
yeah. I'm still hoping that I can do non-native strings that feel good enough that they feel like strings. I think I can do that. And that's an experiment for me to try. It's like, this is a doable thing. So I think I can make strings be non-native and also stringly enough that you'll be happy to use them.
My understanding is Go doesn't really have like a native string, or am I correct? Like I think you have string literals, but I guess you don't have like, or all strings are basically just byte slices. Is that correct?
I think that a string is much like Java, a little object that points to a a set of bytes. You know, I think they're immutable, if I recall. Don't hold me to it.
You have a length somewhere?
I suspect that's in the not in the backing store.
Okay.
I think the backing store, the characters might be 16 bits too, but I don't know. You know, I'm not sure of that either. It was sort of wasn't my wheelhouse, you know.
So do you know if the add, like you have a string add concatenate?
Yeah, yeah.
And then that's a part of the parser for Go, as opposed to have an operator overloading situation on a native stringy object. No idea. Fine.
No idea. You know, I, 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 I dismiss things out of my brain all the time.
Yeah, I have
still
a
have-
question about Go. So recently they introduced generics. Any insight you have about generics and how they approach them?
I know it was the decision was long and tortured. Okay, and basically Go didn't like any of the current solutions. So I think they have some kind of a hybrid solution that sort of picks and chooses between the different implementations that are out there and uses what seems appropriate at the time. But again, you know, I mean, I was, you know, nose to the grindstone on the runtime and didn't look at that. I did have a question. What are people's opinion of Wasm? Is that how you pronounce it? Wasm?
Yeah.
Awesome.
I was my concern. I went through this process of converting GCC to be back end, be able to generate garbage collection stack maps in my youth, and been around for a while. And I haven't seen a lot of success for systems that didn't start out thinking about GC, having them sort of shoehorn them in at some later time. And it seemed to me to be less of a technical problem as a sociological problem. You know, if one group is driving the whole system and another group wants GC and they're not in the driver's seat, it just never, it doesn't seem to happen in my experience, because we were ready to give GCC a complete modular 3 runtime backend with garbage collection, and they just said, basically, we don't care. We're into C and some other languages, but not garbage collected languages.
And we're being used for Linux kernels, and kernels can't have GC, so you know you're barking up the wrong tree.
Yeah, and we're going to change our kernel stuff any way we want, and if it screws GC, then
yeah,
you know, and there was nobody to say no, you can't do that. I just don't know whether Wasm has that same power structure or not.
It's got I think a narrower goal. It's to run within the browser sandbox more arbitrary shit than just JavaScript, but you know that you're running inside of a sandbox.
Well, Java had the same goal in year 0.
Yeah.
Okay, and it grew out of it. You think Wasm's going to grow out of it and actually become
not right now. I mean, that one's okay. Yeah, I'm not going to make a prediction there.
Okay.
You know, predicting the future is always fraught with something dangerous.
You could do that tomorrow, right? Yeah.
Yeah, exactly. The weatherman can't tell me when it's going to rain up here or not tomorrow. Why are you asking me about Wasm?
Wait 2 days, it'll tell you what it's going to be like tomorrow.
Yes, exactly.
Okay. Just a random question.
No, he's got an uphill, I'll say Ben Titzer's pushing. He's got an uphill fight, in my opinion. The browsers are everywhere. It's a useful sandbox. Do I want to run Clojure inside a browser? Well, I can, but do I want to? You know, maybe it's the new, OS for something, maybe, but still seems kind of like I said, like an uphill battle. There might be something come out of that. I would have not have seen
And
the
there are
browsers get
weird.
so dominantly widespread.
Maybe useful in applications like software as a service if you would like to run something quickly, like in Amazon Lambda, and then you don't want to wait for startup time. So it's basically a portable binary IR. It's kind of maybe more competing with LLVM IR rather than with other IRs.
We
So
need a
it's not,
runtime for it.
I have heard a funny description that this is basically a portable IR that is not for the web and has nothing to do with assembly language. That's why it's called WebAssembly.
Okay, I hadn't heard that aspect.
Yeah, but to some extent, if you look at the history, so Chrome launched Knackle. We want to have this native client that enables you to run code compiled directly on the web. And then the second generation of that was, oh, it turns out people have different CPUs. Who knew? And they made pknackle that was going to be their portable native assembly that shipped around LLVM bitcode and just did the last bit of compiling when you got to the server. And then they realized that it was actually kind of hard to ship LLVM inside of the browser. And then they shipped WebAssembly to be like, okay, we are going to target a thing that is specifically designed to be an intermediate that comes down from languages and then can go down to chips.
Nitpick, there was the whole like Firefox on the side with assembly.js and then
Right.
actually
So
getting to
some
Wasm,
extent, it is a descendant of LLVM bitcode as a way to represent what was happening between languages and hardware. And now they're in this weird place that they're being pulled in kind of three different directions because the browsers want to use it to get safe execution of arbitrary code in the browser. And the telcos are convinced that they're going to use it to get safe execution of local client code in the cell tower. So you can get more battery life on your cell phone by running large chunks of your web browser in the cell tower and having that talk to your phone.
Wait a second, I got a complaint there, but you go, Karen, do your third.
And the third is there's a bunch of crypto Web3 communities that are like, this is going to be the VM that we use for executing the crypto contracts in absolutely secure, deterministic ways.
So the guy who lives in the mountains and the winter storms come and they blow over and the 80-mile-an-hour winds push a tree down and the power line falls, how long until the cell tower runs its battery out? Well, its generator goes for like 2 hours and they can't get a diesel refueling truck up there. So then the cell tower goes down and I can't even make a phone call from my house. I can't
And you
call
don't think running a
911.
bunch of VMs will improve that situation?
Exactly. That's what I'm saying. The thing that is currently the fix is that when the weather's coming, they're supposed to go top off all their large generator tanks before it hits, but that happens or it doesn't, or maybe not, or whatever, it's a very hit or miss situation.
I had not heard this telco thing. That sounds wild.
Take my
Do you not
no
want to
denial
have
of
service
service attack
workers for
open
your web browser
possibilities
that are running
there.
in the cell tower?
Yeah, like can I outsource the whole like browser the whole browser thread basically? Like maybe let me do the rendering, but all the other thing you can do.
Can I
I
buy
believe the
100
boundary
burner
is a
phones?
service worker. You launch a service worker on the cell tower, and it speaks with your general thread in the same API that you use to talk to service workers.
So I buy 100 burner phones. I put an app that's designed to burn cell tower battery as fast as possible and just makes new requests constantly. I throw a burner phone at the base of every cell tower. They're throwing them out my window of my car as I'm driving by, kind of bring an entire metropolis down by having every cell tower be unresponsive to every other one. I mean, this
Well,
seems
first
like...
off, you shouldn't make random requests. You should mine some kind of cryptocurrency and send it to yourself. But
absolutely. I'll do something useful, dumb. But the little phone's got like 3 days with a battery life, and I'll just throw it out the window as I pass by the cell tower, and then the cell tower will melt down. Well, when his
You'll need
500
more
neighbors
than
melt down, the
100.
city's gone. I mean, the city communication goes. This is like, wow. I can't see any problems with this at all. Holy moly. Okay, fine.
Actually, yeah,
This should
predicting the
not
future
be
of
video
Wasm is hard.
recorded. How to bring down your Metropolis telco systems. Not the right plan for a public forum here.
I actually had a like fairly basic question about Go's heap. Do you when you do allocation on the heap, or when structs are allocated on the heap, do you need a header for the object, like a heap header, or do you statically know basically what all the places and all the types of the data allocated on the heap?
No, we don't have headers, which is one of the reasons
Okay.
we can pack them into arrays, inline them into arrays, and you can you can create structs of structs and stuff like that, and point to the inner struct just fine. The question remains, how do you find the pointers? How does the GC find the pointers, which is interesting. In Java, you take the type header and you go off to some encoding. It's very fast. In Go, we have a bitmap, okay, that basically tells you 1 bit for every 64 pointer slots, okay, and it'll say 1 or 0. It's cleverly encoded. Used to be cleverly encoded by me, but someone more clever than I showed up. Okay. And so, and there's all kinds of optimizations, things like, it's just, if there are no pointers in a struct, we actually allocate them in their own size segregated blocks. And then if we hit one of those blocks, we know that we don't have to go and look for pointers. Now, the question then becomes, what happens when you scale a program? And this is a thesis that has nothing except my guessing. My theory is that as heaps get larger, and by that I mean really large, a lot of the stuff doesn't hold pointers. Okay, that a lot of it is just these bitmaps and other non-pointer data. Now, you can obviously write a program where that's not true, but so my theory is that this approach to using bits probably scales fairly well. Okay, so yeah, if half your structs don't have pointers, and again, since it's a value-oriented language, unlike Java, most of your structs have inline structs in them that don't have pointers. So we sort of win on win on win. With Go wins more so than say Java would win in using this approach. Does that answer your question, or more than you wanted to know, or?
That more than answered my question, but wasn't more than I wanted to know. So perfect.
Okay.
But I actually the scaling question does bring to mind that one case where I would imagine that not having pointers isn't actually the truth is things like social network graphs. This comes from hearing a talk this past February on succinct data structures. Basically, like when you're storing things like the Facebook connection graphs or social network graphs, or when you're for some reason storing all of humanity's Git history plus any other basically VCS version control system graphs into a single database. Here you end up with a fairly large amount of data, and then you want to compress it down very aggressively, and their succinct data structures are all the rage. But then in these kinds of graphs, because they are kind of pointing forwards and back all the time, there I would guess that pointers actually are fairly common between the structs. And I would guess those are also one of the bigger data structures that humanity has, aside from financial and physics research related data, I guess. The latter
Anybody
two.
who has columnar data of any kind, so lots of physics, but there's plenty of domains like timestamps for sensors and shit, where you get very large collections of highly compressible data that wouldn't typically have pointers. That's a common
Yeah, those like physics data and
IoT.
IoT monitoring financial stuff. That is definitely like not pointers. But then when it goes to social media graphs or that kind of stuff, I would guess there actually you do have a lot of pointers going back and forth.
So you can also change from pointers to indices into arrays, the Rust solution to get rid of pointers. But that's the user making a decision about how to wedge his data structure into your less than pointer friendly language. Yeah.
And stuff grows bigger than one computer. A lot of those things have these highly interlinked data structures, but all of the references are some foreign key snowflake-like object. Give me a 64-bit number that's unique across the entire organization, and I'm going to use those as the IDs for every object in the world.
Yeah.
You know, every object in S3 gets a 64-bit number that is unique against every other object in six. So you end up with a lot of maps and hash tables that go from object IDs to objects rather than pointers.
I have a timer limit coming for me.
Okay.
So I'll take short things here. People want
You
to
can
ask.
hide anything behind a pointer in direction.
Sorry?
You can hide anything behind a pointer in direction. So I'll leave you with that.
Every performance problem can be solved by removing a layer of indirection, and every computer language problem can be solved by adding a layer of indirection. Yeah. All right. Well, this has been a fantastic meeting.
It was fun.
I had a great time.
And thank you for Go. I've used it to solve problems.
Good.
Yes. Thank you for Go.
Good.
Thank you for
Even
Go. I haven't.
TypeScript, right?
Yeah, I was going to say I haven't used it to solve a problem, but it's going to solve a problem I have.
Yeah.
With TypeScript.
All right.
Yeah, watching the TypeScript people decide to switch to Go. When someone who's writing their own language decides to port their project from the language they created themselves to your language, that suggests you have definite value add.
Wait till April 1st when we announce Rust is rewriting their so we're gonna need some backup from you guys when I put the
No, I definitely want that April 1st.
Yes,
Rust.
I'm ready for it. All right.
That's a great April Fool's joke.
Okay.
Till we meet again. It was very fun.
Yeah.
And bye.
Bye bye. Thanks.